name is Alexandre Florio. I'm presenting this work on large-scale dynamic vehicle routing with stochastic requests. And this is a joint work with a fellow postdoc from Eindhoven, Jan Zank, and also a postdoc from the Mathematics and Computer Science Department in Eindhoven, Kelling, and my supervisor, Tom. We have some online resources for this project. You can find the preprint at the archive link for the preprint. You have a GitHub repo with all the implementations and some visualizations. And there's also a YouTube video here with some visualizations of a couple of policies that we implemented.
You can take off your mask so we can.
You can take it.
Yes,
okay, great.
Yes,
so
you feel comfortable.
Yeah.
And we should,
all right, and so what is the general setting motivation here? We decided to study this dynamic VRP with stochastic request, which is pretty much the canonical version of dynamic vehicle routing problem. So you have a set of static or planned requests that you already know in the beginning of the service period. And you have requests that arrive dynamically during the service period, and you have to decide what to do with those requests. So a request is just a pickup location or a service location. So it's not a pickup and delivery context, it's just going to the place, serving the request, and that's it. And you have multiple drivers and vehicles. And the only constraint that you have is that all of these vehicles, they have to return to the depot before the end of the service period. And the goal is to serve as many requests as possible. So this is pretty much, as I said, the prototypical version of the dynamic vehicle routing. And you can see here just how it looks on a snapshot of a simulation. You have a lot of vehicles, and you have a lot of requests that you already served, those green dots. You have requests that you have scheduled to serve, and you have new requests. So one request here appearing dynamically, and you have to decide what to do with those requests. There are a bunch of papers on this class of problems. Just to name some of them, you have a pretty good and updated review on the problem, recent EJOR paper. So if you are interested, you can refer to this paper, to this review paper. But just to illustrate here what we're doing, we try to scale up the solution methods for solving this problem to really large instances, at least much larger than what was considered in the literature before. Both in terms of number of requests, but also in terms of number of vehicles.
What does it mean, RT?
Sorry?
RT, what is it?
RT is what is real time. So this is, at the moment that the request arrive, in our context, you have to make a decision. It's like the customer is calling in, and you have say, okay, I'm going to serve your request. I'm not going to serve. So, but you have to give the decision at that moment. There are some works that they consolidated the decision epochs at the moment that the vehicles arrive at the node, and this real time doesn't happen. So this is also a characteristic that we have here. For the methodology, we formulated these problems as sequential optimization problems, so a sort of MVP model. And we propose that our main contributions is a stochastic look-ahead policy for scheduling requests. But we also propose in the paper column generation based in heuristic for deriving initial plans for serving the static requests. But I'm not talking about this part in this talk because there's time limitation. So I think it's more interesting to focus on the dynamic part. I will introduce some notation, try to be as light as possible. So you have a street network graph. This graph G, you have a set of intersections V, you have some road segments A, you have the depot identified by node 0. You know the duration of fastest paths in the network, so you can pre-compute all these shortest paths and you know the duration of those paths. And the service period is represented by this interval 0 to capital U, and you have a fleet size of capital K vehicles. You have a set D of U of dynamic requests that arrive up to some instant U in the service period. And the request is represented by this triple U ID, where U is the request arrival time, so the moment when the request arrives. I is the location from which the request arrived. and D is some durations, the deterministic duration that is required for going there and serve this request. So once you arrive at that location, you're going to need this time D to serve the request. And you have this random variable. We define this capital T as the random variable representing the total number of dynamic requests. And we assume that we can sample from the probability distribution of dynamic requests. So in this network, those requests are arriving over time in different parts of the network. And we assume that we can draw sample paths from this spatial temporal distribution. All right, so you can sample from the request arrival process. The MDP model or decision epochs, as I just commented, are the moments when a decision must be made. So in our setting, we have to make a decision each time a dynamic request arrives. So a dynamic request arrives, you have to decide what to do with this request, which is either accepting or rejecting. And if you accept, then you have to assign a driver and update the route. So you have a total of 1 plus. So also you have one epoch here for the initial decision, but again, I will not discuss this one. I have a couple of definitions. So a route is just a sequence of nodes in the network, and for each node in the sequence, you have associated with it a set of scheduled requests or requests that you're going to serve once you arrive at the node. And the definition of a budget, which is pretty common in dynamic vehicle routing, is how much time left you have along a route. So the budget of a route is how much time left you have to try to fit all the requests before the service period finishes. We define a state in our dynamic system as, yeah, we're gonna define it here, but to define the state, we need to define the vehicle state. So basically, the vehicle might be either idle at the depot, and this doesn't really happen too often because unless you have an over-dimensioned fleet size, all the vehicles are going to be traveling. So most of the time, you're going to have the state of the vehicle represented by a route, theta k, and tau k, which indicates the moment when vehicle k started to travel route theta k. And with this information, you can map at any moment in time, you can map where the vehicle is. So it's pretty sufficient information for determining the location of all vehicles at any instance. And then the state is just a tuple with that consolidates all the vehicle states. So state of this dynamic system is going to be this tuple ST with one component for each vehicle. And the last component here is for the request that just arrived at epoch T. All right. We have to make a decision once a request arrives. And as I said, you have to decide whether you're going to accept or reject the request. If you accept the request, you have to assign this request to a vehicle. And once you assign the request to a vehicle, you have to determine how you're going to update the route of the vehicle to serve this request. We consider, if you go back here, you see that for the acceptance is at either 0 or 1, assign that you have k possibilities, capital K possibilities. But for routing, there are combinatorial number of ways that you can fit a request in a route. So you have to narrow down that a little bit before you can try to propose something that is tractable. So we consider two policies. The first one is just the cheapest insertion, which is pretty much standard way in dynamic vehicle routing. But we also try the complete reoptimization, which is you insert a request in the route and you completely reoptimize that route in order to maximize the budget.
Can I interrupt you a second?
Sure.
Sorry,
something on the way?
Yes, this, which wasn't working. And here we are.
So, okay, thank you. So for the state transitions, you have your moment that you are at state ST, you have a set of possible decisions XT. And a policy is nothing more than an algorithm or a function or a mapping or a table or whatever that maps the state to a decision within the set of possible decisions. Once you make a decision, you're going to transition to another state, and you have this transition function, which is so. And I'm basically using the Powell's notation for representing this sequential problem. Everything that happens in your model is going to be represented by this Sn transition function that will take you to the next state as t+1. And you have this kind of operational constraint that these decisions must be taken in real time. So when I say real time here is that you have to make a decision seconds. You cannot like take several minutes for processing and for returning a decision to the customer. So you have to answer as fast as possible. Finally, we have rewards. So if you accept the request, you have a reward of 1. If you reject the request, you don't get any rewards. And the objective is to maximize the expected number of rewards. So you have to find a policy within the set of all possible policies. You have to find one policy that is going to maximize the expected number of rewards. So here you also have, you see that the formulation here also takes into account the initial decision. But again, this Y part here, we are not going to discuss in this talk. Okay, so this is the MDP formulation. And then I'm not, for the remainder of the talk, I will basically discuss this PBP policy, which is the method that we propose to solve this problem and to try to maximize the number of accepted requests. For that, we define first this potential. You might as well call it the value function, which is given a policy and a state ST. What is the expected number of requests that you're gonna accept in the future, given that you are at this state, you are going to apply this policy. So it's a sort of a value function for all. For a given state, or look into the future using a given policy, how many requests you expect to accept. And it turns out that if you have a good approximation of this value function, you can generate a set of candidate decisions, which is a subset of XT, and you can select the decision that maximizes the expected reward. Yes?
So, quick question. So, is the expected number of clients that you're going to accept, or the number of clients that are going to propose? Is the offer or the demand? The expected offer or expected? Like how much you will be able to?
Is the expected? You want to maximize? You mean the definition
Yes.
of this potential?
Yes.
Yes, it's given. Yeah. So if you have a fixed policy and you are at a given state,
Yes.
and you just use that policy until the end of the service period,
Yes.
how many requests you're going to accept on average?
Okay.
That's it.
Okay.
Yes.
Just to be sure to understand, so the goal is just to maximize to satisfy both demands.
Yes.
Okay.
Yeah. In expectation. Yeah.
Okay.
So basically, the idea is that if you have a good approximation of this potential here, or the value function, you can generate a bunch of candidate decisions, X tilde, at epoch T, and you can select the decision that maximizes your immediate reward plus the expected reward goal. So everything boils down to have a good approximation of the potential. And then this expectation here you can figure out by doing some sample average. All right, so now our goal is to get a good approximation of the potential. And again, the only thing that we have available is that we can sample trajectories from the true spatial temporal request distribution. In this particular problem, when you start trying to learn the problem, what are the trade-offs in this problem? There are two challenges that you have to overcome. So the first one is, if you have a given state in the system, how are you going to estimate the budget or the amount of time that is going to be required to serve a request in the future? Because in the future, your state is going to be completely different. So your vehicles are going to move, new requests are going to be accepted, the routes are going to change. So how are you going to estimate the budget required for serving a future request? And the second thing is, how are you going to handle the competition of vehicles to serve requests? So if you have a lot of vehicles in the network, in the same place of the network, and you have one request appear in that part of the network, you have a lot of possibilities of serving these requests with a lot of vehicles, but only one vehicle will get this reward. And if you want to get a good policy, you have somehow to try to incorporate this competition in your approximation. So just an illustration of what happens here. You see that the states are changing over time. So here you have 500 minutes left, here you have 400 minutes left, and then you have a different state. If you're sampling requests in the future, you want to estimate the budget for serving these requests. How are you going to do that if the system is changing over time? So again, when you start looking at the problem and analyzing what's happening in those simulations of simple policies, you see that there are two things that always happen. First is all the vehicles are going to return to the depot at an instant that is very near the end of the service period. And the reason for that is that you want to maximize the number of accepted requests. So you're going to use all your time available for serving requests, and you're going to return to the depot at the last possible instant. And the second thing is this request order preservation, which is the relative order of scheduled requests does not change over time if you apply the cheapest insertion policy by design, right? The cheapest insertion, you're just finding the place to insert the request along the route, but you're not changing the order. So this is by designing the cheapest insertion, but also when you use the reoptimization policy. So when you solve this open TSP and reoptimize all the requests along that route, you're going to observe that most of the time, also the relative order is not going to change. And if it changes only slightly. So we're based on these two remarks, we're trying to capitalize on that to come up with a good approximation. So those two remarks, they suggest this concept of effective speed. So the idea is to try to predict the location of the vehicle in the future. So you are at a given instant doing in your dynamic system, and you want to predict what is going to be the location of this vehicle, let's say 1 hour, 2 hours ahead. And this concept of effective vehicle speed is helpful for that. So we define this effective speed as the speed of the vehicle such that if the route of this vehicle doesn't change anymore until the end of the service period, then this vehicle is going to arrive at the depot exactly at the end of the service period. All right, so the vehicle is traveling the network at a given fixed speed. And we'll have some budget available. So we're going to decrease the speed of this vehicle such that now this vehicle is going to arrive at the depot exactly at the end of the service period. All right, so the effective speed is a speed that is lower than the actual speed of the vehicle. And you have a closed form expression to compute that. And once you calculate the effective vehicle speed and you want to predict the location of the vehicle at a future instant, what you are going to do is you are going to simulate the current route of the vehicle for an amount of time u prime minus u, where u prime is the instant in the future and u is the current instant. Right? So you're going to take the effective speed, you're going to take the current route of the vehicle, and you're going to simulate this route under the effective speed for that amount of time. And then where the vehicle ends up after that amount of time is a good prediction of the location of the vehicle. And I'm coming back here because now you can notice this idea of the routes not changing that much. So you see that here you have 500 minutes to go, here you have 400 minutes to go. Here you accept 33 requests, here you accept 66 requests. But you see that those vehicles, they moved. So for example, this vehicle here, this white vehicle here moved. Now this vehicle is here. But you see that the white route, the planned route, didn't change too much. Even though you double the number of accepted requests, those routes are still more or less the same. So if you want to predict the location of this vehicle in the future, we're going to take this effective speed and just simulate at this lower speed for a given amount of time. And once you have a good prediction of the location of this vehicle in the future, you can also predict what are the nodes that this vehicle is going to traverse still along its route in the future. And this is given by this orange. So the notation gets heavier here because you have a lot of vehicles and you have to consider the vehicle states and the instant in the future. But it's just representing the set of nodes that this vehicle K will traverse after some instant U prime. And once you have this set of nodes, you can compute what is the budget that is required to serve these future requests by this vehicle K. So just take the minimum over the set of nodes that is expected to be traveled in the future of the fastest path from the node to the location of the request and coming back to the node plus the duration required to serve the request. Okay. So you have, based on that, we solved the first challenge that we anticipated here, which is estimate the minimum budget required for serving a request in the future. How we do that? We define the effective speeds. We predict the nodes that are going to be traversed in the future, and then we take the minimum over all these nodes of the fastest path from the location of the vehicle to the location of the future request and coming back to the route. But we still have the problem of handling the competition among vehicles to serve requests. So to do that, we explore some sort of knapsack view of the problem. And this is if you estimate, let's suppose you estimate the potential by taking the sample average over a number of optimal solutions to a knapsack problem. Where this knapsack is, you take a sample path, and you have those variables here, which ZKR, which is whether you are assigning this future request R to vehicle K. So you want to maximize the number of future requests that you accept, subject to the constraint that you cannot exceed the budget for each individual vehicle. And you can only assign a request to a single vehicle. So since in this formulation you are taking all the vehicles at the same time and you can only assign a request to a single vehicle, you are handling the competition of vehicles to serve requests directly here in this model. All right, so this solves our second challenge, right? So we are not optimizing for each vehicle individually, but we are creating a model that optimizes for all vehicles at the same time. So if you have a lot of vehicles in the same area, doesn't really matter because you can only assign that request to one particular vehicle. And you want to maximize the number of accepted requests or your prediction on the number of accepted requests. And you handle the expectation by taking the SAA here, the sample average approximation over all these models. And by the way, these are just, I call it knapsack, but this is more like continuous knapsack. It doesn't really matter too much if just having the approximation. If you put binary variables here, then it gets complicated to simulate that because we need the real time. Okay, so now we have the policy, this PVP, which is we initialize a set of 10 decisions with just the reject decision. And then for every vehicle that can serve that's able to serve the request, we are going to create one candidate decision for assign the request for that vehicle, insert that in X2T, and then you are going to return the decision that maximizes the immediate reward plus our estimated reward to go based on 8 solutions to our knapsack model. Okay, what does it work? So the first question is that we have a pretty good accuracy of the reward to go using this policy. So even at the beginning of the service period, your estimation or your approximation of the reward to go is within 2.5% on most instances. So even like 10 hours ahead, so you just started, you haven't accepted any request yet. So you just have a set of planned routes. You can already anticipate, you can already estimate with a precision of around 2.5% what is the number of requests that you are going to accept in your instance. And these are highly dynamic instances with 95% degree of dynamism. So it's pretty fast. So you just need to solve a certain number of linear programs. And you have no tunable parameter. There's nothing to learn here, right? 0. So you just set your value of H and you're good to go. The cons is that it's not so fast. So if you have a very large number of vehicles and very high request rates, your sample paths are going to be really heavy. So those linear programs are going to take some time. We propose another policy in the paper that trades off a little bit the accuracy by efficiency, the SPDP, but I won't talk about it. And what sort of policy is that? And after we created this policy, we observed that it was performing really well, and we tried to fit this policy into some framework of sequential optimization. And it turns out that this is a recent paper from Paul was really good because we were able to classify our policy. So we say that our policy is stochastic look ahead, where we use a strategy for sampling, stage aggregation, latent variables, and policy approximation to come up with a good approximation of the reward to go. So if you're puzzled with all those terminology, then I recommend you take a look at the paper. All right, so let's see, take a look at some results. So we compared against, so we have some greedy policies, accept all feasible requests. Then we do rollout on the greedy policies. We do some policy function approximation where we have a single parameter that we learn offline, which trade off the immediate reward and reward to go. And also a rollout version of PFA. And by the way, PFA and rollout are two of the most used policies in dynamic behavioral. So we define this set of benchmarks to see how we were performing. We considered, Real Street Network of Vienna, 10 hours of service period, number of vehicles from 2 to 20, request rates from 0.2 to 1.5. So our smallest instances with 0.2 are already larger than most instances considered in the literature for this sort of problem. And a degree of dynamism of up to 95% and three request distributions, just to see if we could perform well in all of that. So we get all the combinations of simulations that we performed, so a pretty high number of simulations. And so we get the average number of accepted requests for each policy. And also here I have the two offline plans, but I haven't discussed those two plans, but you can see that the PBP is performing better no matter the initial plan, and by a large margin compared to the other policies. And this is interesting because it measures the acceptance rates, so the blue bars, and the maximum decision times, because again, remember that we want to get this real-time decision. So if you are getting a really good acceptance rate, like for example, this rollout on PFA is quite good. You have pretty good, but then you take a lot of time to compute your decisions. While for the PVP, you get even better, but much less time. And these are for the smaller instances. When you go to the larger instances, then you can't really do rollout anymore because those simulations take too long. And then you have to reduce the number of trajectories that you're simulating rollout. But when you reduce the number of trajectories, then your rollout is not really performing well anymore. So for the PVP, you get much better and at less time. But even for the PVP now, with the very large instances, it takes considerable time. So we have this simplified version, which only considers single knapsack models. Is a good trade-off for optimizing acceptance rate and also doing that fast. Okay, so I have some acceptance profiles, and so this is just the acceptance of requests over time, and you have how good are the predictions of the reward to go during the service period. So just to conclude, the main contributions is basically these models to estimate the reward to go, and by deriving these good approximations, you can also derive those high-performance scheduling policies. And you have a lot of possible extensions here. You can consider pickup and delivery, time windows, multi-period, and so on. You can even consider assignment of requests among these, but this might complicate your job considerably. So I don't know if this is. But for the other extensions, time windows and pickup and deliver can be almost readily incorporated into the knapsack models, because maybe just linear constraints that you need to incorporate when predicting the reward. All right, that's okay. Some acknowledgements here that funding and OpenStreetMap data and cluster, Dutch cluster for the experiment. And that's what I had to say. And thank you so much for your attention. And if you have questions, I'll be ready to take them. Thank you.
Any questions from the audience? If not, we have a Zoom question. So we'll start with this. So any comments on DFA-based policies, for example, linear approximation or neural network, NN, I don't know what the NN is, NN approximation?
I don't have results for that because we have not, we're doing that, okay? But we don't have the results for that. But I can tell what I feel what's going to happen. Okay, so maybe it's not going to be sufficient for the answer, but at least my feeling of working this problem for several months. If you get the PFA has just one parameter, If you want to tune this parameter in the largest instance, it takes 10 minutes for tuning just one parameter. So I imagine that if you have a bunch of parameters and you want to tune all those parameters, it's going to take much more simulations offline. I don't think you can train, even if you have a good representation of the state space in terms of a lot of variables, and you want to train a neural network to try to estimate your reward to goal, depending on the number of parameters, you're going to be stuck in your offline simulations forever. So it's well known that VFA will not work well if you have a lookup table. If your state space is increasing too much, you cannot store this lookup table anymore in your memories. You're going to grow exponentially. There's the question of the competition of requests, vehicles for requests. I don't know how well these deep learning methods could handle that. So that, and on top of that, I think Paul has a good discussion on that. I think this paper that I mentioned, there is also the question of how to use deep learning approximations for VFA, and why this might not work so well for the type of problems that we study in transportation logistics. So I also recommend taking a look at that. But it's mostly based on my feeling on the problem. I don't have the results to corroborate that.
But really fantastic visualizations, but have you shown it already, or finish showing this one?
You came late. I anticipated the online resources. We have some online resources for this.
Okay.
So if you happen to be interested in this problem, and you think, why not try? So, for example, a deep neural network. You might be interested in trying deep neural network because I'm pretty sure that the deep NN will do better. Come here. You just need to implement an interface. And then you can use the simulator to try a policy, right? In the same set of instances. Everything you can compare directly with the results you have. So you don't need to implement all the benchmarks again. You just need to implement your policy. You come here and then you learn how the simulator works, and you can try your new policy on the same, exactly the same instance. So it's everything is here. Yeah.
Yes, I have a question. If you can go back to the slide where you presented the reward, like because one is do you know like what could happen if, like, for example, every request will have a different reward? For example, if probably it's like a bigger order or something like that, would it change a lot, like the model? Or?
I don't think anything changes. You just need to this now is a function of t, right? Reward of request t, so some VT value of request t, and the second thing is here in the multiple knapsack model to approximate the reward to go. You also need to put a weight here on the value of serving this request in the future.
Okay, and then you also have to predict like what would be the request of future requests.
Yeah, this is the same. This is, you can still use the concept of defective speed, and then everything is the same.
Okay.
Should work for this case. At some point, because we could also generalize for that, and then we have another letter in the model, and the notation was already really heavy, so we tried to, but it's a straightforward extension.
Thank you.
maybe ask you like just a little question, then we move on. So you solve this kind of, I would say, knapsack problems because still you have a constraints, and if you don't consider like the cardinality constraint, they are still a knapsack. But you solve the linear relaxation because you want to get a bound. And correct me if I'm wrong. So if you had to solve the binary version of the knapsack problem, your approximation may turn out to be better. May. Okay. Have you tried this out of curiosity?
No, I haven't tried that.
Okay.
There are some results because knapsack is we only know that like, most people know the tip of the iceberg. The knapsack, there are a lot of variants, and there's I think a recent book on that by I don't remember, but there are reasons to believe that the continuous relaxation here offers a pretty good bound on the optimal solution.
Okay.
Because of the number of items that you have in the knapsack. So you can relate that to the theory and say that you are not losing too much or in terms of the optimal solution value of this model by considering the continuous constraints. And on top of that, you are doing an approximation anyway. What is important is to compare them, because if this is a good surrogate, you don't really care about the optimal value.
Yeah.
You just want to find which vehicle is the good one.
How big are the knapsack you're solving? How many variables could there be in this?
We get up to 20 vehicles, 20. So, and in the beginning of the service period, I have 800 requests. So you do 20 times 800 variables.
It's a considerable size. So,
yeah, but with solvers, you can do that in no time.
Okay. I think nobody has a question.
Okay, thank you again.
You've been asked if you can share the links that you had in the chat after, or you can send them to me and then I can.
I will do it now.
Yeah. Okay.
Can you put me as an animator?
Yes, I
Note,
will
okay.
make you co-host.
Oh.
Hello, Alexandre. I have a question.
There's a question. Yes?
Sorry?
Sorry, Alexandre, il y a une question pour toi. There is a question for you.
Last question for
There is a question for you.
okay,
Can you, while we are trying to.
Sorry.
Sorry, cannot do it.
Sorry, I'm a bit slow. I was wondering why you're not minimizing the distance as well in your reward function.
The setting that we consider, we just care about optimizing the number of accepted requests. So it's not, it's the more prototypical version of DVRP. So the most studied version is where you have those vehicles, they have to return to the depot by a given deadline. And you want to be able to serve as many requests as possible within this time span.
My question is more like, if you minimize distance, can you serve more customers? Because if you don't minimize it, maybe you have ugly routes and you cannot fulfill as many requests as you want.
Minimizing the distance is equivalent to maximizing the budget. Is one thing that is important, but it's not the only thing. So if you have just one vehicle operating the network, then minimizing the distance or alternatively maximizing the budget seems to be a smart decision. But if you have multiple vehicles, there are other trade-offs there that if you don't consider, then you might end up with bad decisions. For example, this competition of vehicles in the same area. So it might be worth it to spend a little bit more time, send the vehicle to another area to avoid competition with other vehicles that are already there. So because then you have a better coverage of the service area and you can improve the number of accepted requests.
Maybe. Thank you.
Okay.
Okay.